Hello, class. I'd like to say that this is one of my favorite lectures, Telegraphers Equations, and we'll talk a lot more about what the result of the Telegraphers Equations are. And I'm not going through, of course, as much detail when I do the derivation of the Telegraphers Equations and show you how it all comes out, but that's why I did that earlier sort of derivation of the RL series circuit. I think that might have even been the last lecture that I did. And going through that in all of the examples to explain, you know, what the derivative of e to the j omega t was and everything else. Okay, so let's get to what the actual Telegraphers Equations are, and then how they can be manipulated to figure out to tell us characteristics of the transmission capabilities of the channel and everything else. So let's just look at what they are. So it's minus the partial derivative of v zt with respect to z equals r plus I as a function of z and t. And you're probably understanding, I'm going to finish this first, plus L partial derivative of I of z and t, right? Oops, sorry. With respect to t. Now, if you're looking at these equations, you're probably thinking, okay, well, of course they're partials because these, the voltage there is a function of z and a function of t. And that's what I wanted to do in, I believe it was the lecture before the last lecture, 33, where I talked about how, you know, the wave is changing in x, but then it's also changing in time because the wave is constantly moving at the speed of light in this direction, right? So at any individual point, like let's just say, you know, this line right here, right? This is my line, my x value right there. Now, I don't know how to get that off there when I do the rest of the lecture, but let's say that's my x value. Well, that x value, look at just the value of the line here as it's going. As it's moving in time, the value for this x is changing, isn't it? Constantly as that moves along. And so we are changing both in x and y, or x and time. So that's why we've got to look at this as a two-variable function, right? Now, that's only the first Telegraphers equation. The second Telegraphers equation is minus the partial derivative of I as a function of z and t with respect to z equals, that's a partial, g, and we've talked about, you know, times v as a function of z and t plus c, partial derivative of the function of v of z and t with respect to t. Okay, so those are the Telegraphers equations. And we have to solve those Telegraphers equations to figure out how a waveform, an electromagnetic waveform, attenuates and loses energy as it propagates through a channel, right? A metallic, basically what this is talking about, the Telegraphers equation, is for metallic conductors. And that's, you know, that's what we're looking at for a huge amount of, and air, for, you know, what we're doing with electromagnetic waves. So let's take this a step further then. I want to show you some notation that I'm going to be using. I'm going to say that when we look at the function v as a function of z and t, that's going to equal the real. See why I've got to introduce all of this higher, you know, order mathematics. So before I could really talk about the derivation of the Telegraphers equations. A function of voltage as a function of z, and then e to the j omega t, right? Why do I say e to the j omega t? Because e to the j omega t, of course, is cosine omega t, which is the harmonic motion that's going on sinusoidally in the time domain. And then we've got another voltage of z, of course, that as going down the z thing. So we've got things changing with time and with distance. What would this actually come out to? This thing right here, and let me box that in with blue, because I want to call this so that I can I don't have to keep writing this over and over again. I'm going to call this something so that I can refer back to it without having to write the whole thing out. And what I'm going to refer to it as is V sub Z with a line over the top of it. So the line basically, it's not an arrow, it's just a line. And that line is saying it's changing with time, really, in this fashion, sinusoidally changing with time. And the Z means that it's changing in the Z direction too. All right? Now you could also say that this right here, this real of V of Z, e to the j omega t, if I wanted to, you know, just write that, I could say that that would be equal to V of Z cosine omega t. Does everyone see that? I should just put a box around that up in that top thing there, because those two are equivalent. Right, because I'm saying the real part of this, e to the j omega t, and of course e to the j omega t is cosine omega t plus j sine omega t, right? But the real part of that would be v of z, function of z, cosine omega t. And so that's what I'm saying. This is changing sinusoidally. Of course it is. That's what I'm saying. It's changing sinusoidally. All right, but it's a function of z too. Okay, now. Having gone through all that, I don't think it's going to be so hard to look at z of t, because I'm just saying the same thing, that that's the real part of I as a function of z, e to the j omega t, and taking the real part of that. But what I want to call that is I'm going to call that I bar sub z. All right, just so that I don't have to keep writing this over and over and over and over again. And now that we've got those out of the way, there's your Telegraphers equations, and there's the two functions for voltage and current along the transmission line. And so let's rewrite those now, knowing all of our new mathematics and all of that. Let's go back to the original equations and rewrite those in our new format. So I've got minus the partial derivative of v sub z with a line over the top of it with respect to z equals, right? R plus j omega L times I bar sub z. I'm gonna give you a second to look at that and to make sure that you understand how I got from here down to here. Now let's think back on that last lecture that we had where I did R times I of t plus L di as a function of t with respect to t. You know, and that equaled the real derivative of v with respect to z, right? So, or no, I think it was just the voltage. So I can refer you back to that lecture or to your notes from that lecture, and you know, and look at how I went through there, and look at how I got that j omega, because that j omega is really just the derivative of e to the j omega t, right? If I take the derivative of e to the j omega t, it's just going to be j omega e to the j omega t. I can't even write it up there. I'll try and write it here. The derivative with respect to t of e to the j omega t is j omega times e to the j omega t, as you know. So that's how I could sort of use the derivative of that. The only thing that's different now is this didn't have a derivative. That was just I of z of t. And this did have the derivative of I as a function of z and t. And so that's what I got. That's my first equation right there. And what will the second equation then look like? I think everybody can sort of figure that out. That's going to be minus the partial derivative of I sub z bar with respect to z is going to equal g plus j omega c times v sub z bar. And that would be my second Telegraphers equation written out in our new notation that we're using, knowing that we're using the exponential form for all of these. And I've taken you through that before. I think that, you know, this, I made it a little brighter. Yeah, maybe I could even lift this a little more. I don't know. Yeah, that's a little brighter too. Good. Okay. So you're probably saying, well, that's exactly how I figured that it was going to be written. Here's my twist, and that's why I need I finally have gotten down to the x, and we no longer need the x for any reason, so I'm just going to have to wipe that out. Now, here's probably what you didn't foresee me doing in my derivation with the Telegraphers equations, because I certainly never saw this the first time I did it. Minus, I'm going to take this equation right here, and I'm going to take the second derivative with respect to z of the function v bar of z. That's what I'm going to do. So, and of course, when I take the second derivative, the 2 goes on the derivative, not on the, you know what I mean. So v bar sub z, and then the square does go on the z. So I'm taking the derivative of this function with respect to that. I still have r plus j omega l there, don't I? And then I bar sub z is going to be the first derivative of I bar sub z with respect to z. Oh my God, where have I seen that before? I know, it's fake, isn't it? I would not be a good actor. There you go. Where have I seen that monster before? He's right there, isn't he? That's right. So, what I basically have is I want to replace that now. So here's what I'm going to do. I'm going to take this and I'm going to replace this with minus, right? Because I'm going to take the minus from here over to the other side. So this is going to end up being R, I don't want to use the whole page, R plus J omega L, right? Times, I'll throw a minus out in front of here, minus G plus J omega C times V bars sub Z. Okay, does everybody see that? So here's what my equation is right now. I mean, forget that middle part right there. I've got minus here, D squared, VZ. So I've got a minus here too. So both of those can turn into pluses, as I think everybody can see. So now I've got this equation right here. I've got the second derivative of V bar sub Z with respect to Z. Second derivative of V bar sub Z with respect to Z, right? Minus R plus J omega L times G plus J omega C times V sub Z bar equals 0. Excuse me, it's the third lecture I've done today, so hey, you know, when you feel like doing them, you should do them, because there's a lot of days I really just do not feel. Although what I did was I went out and I cut the grass in between. So I don't have a lot of grass. So I did my outside work, and then it started raining, and of course that's Murphy's Law. I had rain already. I go out, do something outside, and it starts raining. He hates it. Now, what is this? What is this? This is this. Do you recognize that? Do you recognize that? That's right, that's the wave equation. That's the wave equation, and that means that this thing right here is going to be a complex constant. This guy right here. So what does that tell us? That tells us that my propagation constant, that's what it's called the propagation constant. And the propagation constant, by the way, is this. It's the square root of R plus J omega L times G plus J omega C. Now, on all of these that I've been writing down here, there should be a prime. I'm going to go back and put a prime because when I draw, let's draw the communication circuit. Always remember that G is 0, right? G prime is almost it's 0. I mean, you know, there's not going to be anything that we do in this course where G prime isn't going to be 0. So don't worry about G prime. Worry about R prime, C prime, and L prime. Don't worry about G prime. Everything that we're going to do is, like I say, is going to be. And what's the prime mean? It means per meter, right? So ohm. This is going to be ohms per meter. This is Henry's per meter, so on and so forth. But this is the wave equation. It tells us this is the propagation constant. And it also implies it's a complex constant, and it's made up of two parts. It's made up of the attenuation constant, alpha, plus the phase shift constant, beta. Alpha, we'll talk a lot more about this, so I don't have to spend too much time, but alpha is the attenuation constant, beta is the phase shift constant. Both of those two constants talk about energy dissipation as the wave propagates for two different reasons and in two different manifestations of energy loss to the wave. All right, one's a continuous, well, they're both continuous energy losses. All right. I'm going to leave it there. I wonder how did I do with my time? Oh my God, I really went through those telegrapher equations fast, didn't I? I hope everybody understands what I did here. You know, go back through it. Am I going to ask you to derive all of this stuff? No, but you should understand how I derived it all. We're going to come, this is very important now. We're going to start working with this. And, you know, it's very important to understand obviously where all this came from, because this is all historical, basically. I have increased the brightness, and I think that has stopped a lot of the jerkiness. I mean, the brightness is as bright as I can get it now. No, it isn't. I mean, I could actually go a little brighter, but I think that seems, from what I've been doing here, and it's always, you know, I'm always, when I'm going through this, it's, you know, I'm like the Beatles. Yeah, I'm like the Beatles in Hamburg. So I've got a long, long way to go, long after my death, when any of this is ever seen by anybody else. All right, but it is up on YouTube. So you can always go back and take a peek at it. All right, so I'll leave it there. We're going to follow along sort of on this trail now. We're getting into what I would consider, I think, sort of chapter 8, transmission lines and stuff like that. That's where we're going. We can't cover everything, so I want to cover the most important things and the things that really teach you applications-oriented, you know, orientation to understanding electromagnetic field theory and its applications. And we're doing quite a bit. Okay.